SwayamPrabha. Digital India. Educated India.
Hello and welcome back to this series of lectures on elements of solar energy conversion. So far we have covered 8 lectures and today is the lecture number 9. Okay. So we are almost through about a fourth or a fifth of the whole content, and the initial stage we go a little slow, so that is why it took long, but as we go on our pace will increase a little bit, and as you have the flexibility of pausing the video and watching it again, so I do not think that will be a problem. So, whenever you feel that things are not getting clear, please go back, look at the older videos or the videos of earlier lectures, and then you come back to the point, so that you understand all of it till that point and you can visualize. The most important thing I always stress, that you need to visualize all these different angles, solar positions, then only you will be able to grow your intuition, and intuition is the thing that tells you that you have learned a subject. Okay. So, let us start with lecture 9. So far what we have covered is the basic concepts, okay, related to sun and earth relationship, and also related to the solar radiation, its spectrum, how it varies, the effect of atmosphere and all. So, I am now telling all of those as basic concepts, and now what we have started to look at important angles related to solar radiation with respect to an observer, or rather we are interested in, for a solar collector system, how much radiation we can expect and all those things, and that is why we are interested in these important angles and their correlations. Okay. So, we have covered different reference frames, majorly the observer centric reference frame and earth centric, which means the reference frame origin is at the center of the earth. So, how they are interrelated, that also we are looking at. Okay. So far what we observed, there are two major bottlenecks that we observed where we stopped in the last lecture. First one is, in all our relationship that we have derived so far, we have used hour angle omega for the correlations for the angle of incidence. as we discussed, angle of incidence is a key angle which determines the intensity that is available to that solar collector surface. So, hour angle is what we have looked at, okay. But the problem with this hour angle is it is very local, okay, because hour angle tells you with respect to the solar noon what time it is, right, and solar noon changes from one point to the other with respect to the longitude, right. So, as solar noon changes, from point to point, so as the hour angle, right. So, if that is so local, then it is very difficult to generalize this particular analysis. So, difficult to generalize the analysis, and that is why we need to make something which is more global. That is the first bottleneck we have seen, and the second one is the surface azimuth angle. Okay. So, this surface azimuth angle we have not included it so far. Why we need not include it so far? Because we assumed, and in one case we also mentioned explicitly, that the collector surface is tilted towards the equator. So, this we assumed. That means, we have restrictive assumption regarding the tilt or orientation of the collector surface. Again, this is causing a hindrance in generalizing the analysis. Okay. So, how do we designate the solar azimuth angle? Is designated with AZS. Okay. So, these two major factors we need to get rid of. So, for general analysis, we need to connect this hour angle with the solar azimuth angle. So, if you think closely, then both of solar azimuth angle is designated as AZ. Okay. Now, if you think closely, both of these quantities actually measure similar thing. That means the time with respect to the solar noon. That is what explicitly measured by the hour angle omega, but the solar azimuth angle, it measures on the equatorial plane, okay, with respect to the prime meridian, but in the equatorial plane, not in the observer plane. And so, basically they are connected and we have to establish that connection, okay, and include this surface azimuth angle AZS, okay, in the analysis, so that any orientation can be analyzed throughout the through this formulation, okay, for flexibility in orientation. Okay. So, first let us look at the physical picture. Okay, what do this AZ and AZS mean? Okay, suppose we have a plane, okay, which is tilted by an angle beta with the horizontal. So, if this is the horizontal plane, this beta is the tilt angle, right. So, these designations are very standard. So, please do not use any designation, then it will be very difficult to handle several of these angles. So, whatever you may use some other designation as I am using, but I would urge you to use the same, so that there is no confusion between different angles. Okay. So, if that is the case, let us take a point on this particular plane, okay, and with respect to that point we can draw vertical, okay, and we can also draw a surface normal. This is normal to the surface. So, this is the surface normal vector, okay, and we can also draw the direction of sun ray, okay. So, let us say this is the direction of sun ray, here we have apparent location of the sun, okay. Now, what you can do, okay, another thing we need to mention here is the south direction, okay. As we have talked about, the azimuth angles are always measured with respect to the south direction, right. That is how the solar azimuth angle is measured. So, let us say this is our south direction, okay. Now, what we can do, we can drop projection of these two important vectors, one is IN, the other one is the surface normal, on this particular horizontal plane. So, if we project the surface normal here, and if that projected point is connected to the observer point, then the angle it makes, okay. So, let me use the same color coding so that you can understand. So, the angle it makes, this projection on the horizontal plane with the south direction, this angle is our surface azimuth angle AZS, right. And the same thing we can do, we can project the direction of sun or sun rays to the horizontal plane and connect it to the observer location, okay. So, now again that particular connecting line so basically this particular line okay, is the projection of the sun rays on the horizontal plane. Okay, let me write that explicitly. This is the projection of sun ray on the horizontal plane. Okay. And the other one, this one is the projection of surface normal on the horizontal plane. Okay. Now, the angle this projection of sun ray that makes with the south direction, that we call the solar azimuth angle, okay, AZ. So, in this figure you can see that the tilt angle and both the solar and surface azimuth angles are put together, so that you can visualize the whole picture. Okay. Now, one important angle we want to show here, so that the relationship is even more clear. So, what is the angle between the surface normal and the sun ray? Can you tell me? Please think of it, and now I am writing, this is the angle of incidence, right. So, this is the angle of incidence on the collector plane. Okay. So, now both these angles, both this angle and the solar azimuth angle, both are now oriented or measured with respect to a single reference frame, which is global south. Okay. Global south means from wherever you are, you have to direct the vector towards the south pole of earth. Okay. So, that is a unique thing, and you have to I mean it is general, okay, because that is a global south direction, and you can find it anywhere in the earth, wherever you are interested in. Okay. Now, as we introduced, AZS or surface azimuth angle, now we are in a position to connect this hour angle with AZ and AZS. Okay. And now we are going to use the mathematical relationship that we have taken from the 3-dimensional geometry, that is the spherical triangle relationships are to be used. Okay, you remember the cosine and sine rules that we learned couple of lectures ago, I guess. Okay. So, if that is the case, let us look at this particular figure once again. So, let us say that this is the plane that we are interested in, this is the tilt angle beta with the horizontal, and suppose we are here at this point. Okay. Here is the vertical direction, here is the south direction, and this is the suppose this is the surface normal and this is the sun ray direction. Okay. So, we can have a sphere. So, let us say that we have a sphere centered at this point. Okay. Then if we have that sphere, what will it do? It will have some intersection with these three lines. One is with the vertical line. So, let us say this is the point V, small v, let us say. Okay. And for the surface normal, let us say this is the point N. Okay. And for the solar radiation direction, let us say this point is S. Okay. So, this particular Swayam triangle is the spherical triangle NSV, which connects the points of intersection of the sphere which is centered at the observer location. Okay. So, point of intersection with the sphere with the in the same order. So, to the surface normal and then sun ray direction and the vertical direction. This is I am writing it explicitly, so that you can visualize and think that what is this solar or what is the different angles that will be relevant to this particular solar this spherical triangle. Okay. So, now we will try to locate few angles here. So, one thing is again we can drop these projections. Okay. So, this one will be our AZS, the surface azimuth angle, and then we can also drop a projection here. Okay. So, this angle will be the solar azimuth angle AZ. Okay. And now, what we can see here, this one you have to visualize that this particular angle okay, which is surface angle. Okay. So, this surface angle is nothing but your AZ minus AZS, that you have to visualize and make sure you understand that that surface azimuth angle will be the difference between the solar azimuth angle and the surface azimuth angle. Okay. So, which angle I am meaning here? This is the SVN angle on the spherical surface. Okay. What other angle can we see here is Okay, let me, no, I have to show all the angles here itself. Okay, one thing I forgot, I need to mention, this is the origin of the sphere or the center of the sphere, which is the observer location O. Now, okay, another thing we can write here is the, again this one you have to visualize that beta is nothing but the central angle NOV. Okay. So, what is the central angle NOV? This is the angle, right. So, this is the line that is making a central angle between N, O and V, right, and this angle is this, and it is nothing but beta, because it is the angle between the surface normal and the vertical direction. Okay. So, this is the angle between surface normal and vertical direction. So, that is the tilt angle, right. So, that is one angle we got. The other angle that we can see here is this one. Okay. This is again a central angle. So, that angle is our theta, right, the angle of incidence. Let us say theta t, t stands for the tilted surface. So, angle of incidence on the tilted surface. Okay. And what angle is that? That is the angle between N or ON and OS. So, the surface normal direction and the sun ray direction, that is the angle of incidence, right. And on this particular case, it is the central angle delta or angle NOS, right, that is also a central angle theta t. And the other angle that we can see is this angle. Okay, that is also a central angle, an angle between the vertical and the solar direction. So, that is the zenith angle, right. So, this theta z is zenith angle and it is the central angle SOV, that is a central angle. So, please differentiate between the central angle and the surface angle. So, here we have talked about one surface angle, which is this one, okay, that is AZ minus AZS, and we have talked about few of these zenith angle, the theta t, okay, here, and here it is beta. So, three central angles we have talked about and one surface angle. Okay. Now, let us go to the next page and let us try to say this. So, just to summarize from that mesh, that we have this spherical triangle, okay, okay. So, here what we have is, so this is the spherical triangle we are interested in, and here the central SON is our theta t, or the angle of incidence on the tilted plane, and then so this is angle of incidence on tilted plane, okay, and this is same as the curve NS. Okay. So, that is the arc that we are subtending on the surface of the sphere. Okay. Similarly, the central angle SOV is our zenith angle theta z, okay, and that is again the arc that we subtend, that is SV. Okay. Now, another central angle that we see here, central angle NOV, that is our arc NV, and that is beta, or the tilt angle. Okay. Just we are clamoring all this information from the last page figure. So, if you do not understand any of these bits, please go back to the last page figure and look at it whether you agree with that. Okay. And one surface angle we have. So, 3 central angles. Central angles are this 1, 2 and 3, and here we have just single one surface angle, which is our SVN, and that is AZ minus AZS. Okay. That means difference in solar and surface azimuth angles. Okay. So, now we are in a position to apply the spherical triangle rules. So, apply spherical triangle rules. So, the cosine rule is, we have seen it. So, here we can write our cosine rule. What is that? That is this rule, right? Okay, this is a surface angle, and all other A, B, C, all these are central angles, right. So, what we can write for this particular case? We can write cos of central SON will be equal to cos of central SOV multiplied by cos of central NOV. So, for the first time I am writing all these different angles with central or surface angle, because that way your intuitions will grow. First case you have to see very lucidly. Okay. So, that is why I am doing it. Later I will not mention this central or surface as we use them. Okay. And plus sine of central SOV multiplied by sine of central NOV, okay, and this multiplied by cos of surface. So, only one surface angle is there in the cosine rule. So, that is angle SVN. Okay. Now, we will just substitute what those angles are. Okay. So, if we substitute, then we get cos theta t will be equal to cos theta z cos beta plus sin theta z sin beta and cos of this difference between solar and surface azimuth angle. Okay. So, this is very simple, right. We just use the cosine rule on this particular imaginary circle that is located, I mean that is centered at the observer location. So, this is a very important rule. Okay. And note that no mention of solar hour angle. So, omega is not at all mentioned. So, this is general, right. All these angles are measured with respect to something universal like global south or horizontal plane at particular location. These are universal things and we are talking with respect to that. Okay. So, what we can say that we obtained an expression for the angle of incidence on a tilted plane without hour angle dependence, rather we have the azimuth angles, both solar and surface azimuth angle dependence. Okay. So, this is completely general relation. Of course, we will see that we will need different forms of this general relation, because not whatever is given or measured that you can find from this relation. So, we need to have different forms, but this particular form is indeed very general, right. Okay. So, now what we can say, now we have seen both the sides, but we have to connect the dots, right. So, we need to relate these azimuth angles to the hour angle, right. Even if we do not need it, but we need the interrelationship between them. Why? Because whenever we talk about a solar collector, we have to talk about the time, the local time of that, right. That is how our intuitions work. We do not think in terms of the global scale. We think of the watch that we have, we can at least connect it to the solar time, and then for that local solar time we have to connect to what those azimuth angles mean, because our intuitions work with respect to the local time. Okay. So, that hour angle dependence has to be there. Okay. So, to connect these two, that means this and the difference between these two angles, azimuth angles. Okay. So, for connecting, again we will involve spherical triangle, but now it is not the sphere will be the earth itself. Okay. So, last time the spherical triangle we have taken, the sphere was an imaginary sphere centered around the observer location, right. But here this is not imaginary surface sphere anymore, this is the earth itself and of course centered around the surface of the or center of the earth. Okay. So, that is the major difference. Okay. Let us see how we can use this spherical triangle formula when our sphere is the earth itself. So, now let us draw an earth. Good enough. Now, we have the center here and let us say this is the equatorial plane. Okay, first this is our earth and this is equatorial plane. Okay. And here you can draw the north pole. Let us say the center of the earth is O, okay. And let us say that the observer location is here. Okay, let me use a different color. So, the meridian that goes through the observer location is this, right, and this will be south. Okay. And okay, let me write this is the observer location P. P is the observer location. Okay. Now, if that is the observer location and now suppose we have the solar direction or solar radiation is coming through this point. Okay. So, sun is somewhere here, okay, and normal direction of sun ray that is going directly to the center of the earth, that point let us name it Q. Okay. So, another meridian we can draw through this Q point, right. Okay. So, now one vector can we draw here that through the observer location, if I draw a line through the center of the earth, what will we get? Please, before I proceed, please stop and think what that direction will be, then you switch play the video again. Okay. So, this angle or this direction is the vertical direction, right. Let me write it explicitly, this is vertical. Okay. And so, here you notice that we have a spherical triangle already. So, think of this spherical triangle. Do not we have? Okay. So, this NPQ is a spherical triangle on the surface of the earth. Okay. Now, on this spherical triangle, now we have to find out what will be different angles. Do you know them? Do you recognize them? That is what our task will be. Okay. So, first thing that very easily we can recognize one angle, which is the angle between the so if you connect these 2 points, what angle is this? This is the latitude, right? Latitude of point P, because that is the angle it makes with the equatorial plane. Okay, that is easy. The other thing is that similar way, just for the location of the observer, we have said that that is latitude, but if we think of the latitude of Q, what is that? That angle is, so basically this particular angle. So, basically whatever angle this particular line will make at the center O. So, what is that angle? That is our declination angle, right, delta. So, these two angles we obtain very easily, okay. And the angle between the meridians, that one meridian is going through the observer and the other meridian is going where sun is radiating normally, that means Q, that angle is our this angle between these two meridians, that is our hour angle, right, omega. So, few of these triangles or angles we have directly determined. Okay. Now, one thing we will determine here is the, which is little tricky, so please pay attention. Yeah. So, this particular angle what is this? Let me first write it. This angle is our solar azimuth angle. Why do you say so? Because you see, this is the angle between the south direction and the projection of sun ray on the horizontal plane. So, this projection of sun ray on the horizontal plane is nothing but your PQ. Okay. So, PQ line that is making to the south direction, and can you see that this line is nothing but going to south. So, this is our south direction. So, whatever angle it makes with the south direction, that is our AZ, which is the solar azimuth angle. Okay. So, lot of these angles we have obtained. So, basically now you can see that this surface angle NPQ is nothing but pi minus AZ, isn't it? So, it is a straight line, NS is a straight line on the sphere surface, and so the NPQ, this particular angle is your pi minus AZ. Okay. Another angle we have here is the zenith angle. What is that? The zenith angle is the, let me just explain why we get that. Okay. So, our central POQ or the arc it makes on the sphere surface, that is the zenith angle, right. Why it is zenith angle? Because it is the angle between OP, okay, which is the vertical direction, and OQ, which is the sun ray direction, right. So, this PQ, okay, this PQ, which is the arc on the surface, is equivalent to the zenith angle theta z. Let me write that zenith angle as well, okay, because it is the angle between the vertical direction OP and the sun ray direction, which is OQ. That is why it is the zenith angle. So, again we have obtained, let me go to the next page and let me draw this spherical triangle again as we did in the last case. So, this is our north pole, this is our observer location, and this is the point where sun is radiating normally. Okay. So, what we obtained is that this central angle POQ is our theta z. Now, central angle NOQ is our pi by 2 minus delta. Okay. So, one thing I need to mention here, that okay, this is not pi by, this is pi by 2. Okay, let me just write it again. This is pi by 2 minus AZ. Okay, because the central angle that makes is NO, when it goes to the southern hemisphere, then this whole sign convention changes, and we only talk about with respect to the equator. Okay. So, that is why this is pi by 2 minus AZ. So, this angle is also pi by 2 minus delta. Okay. This is nothing but the arc NQ on the surface. Now, other central angle we have is angle NOP, and that is our curve NP, and this is pi by 2 minus L. Okay. Okay. So, I need to go back. Okay, this is fine. Okay, I am making a mistake here. So, this is pi minus AZ, but here it is pi by 2 minus L. Okay. Now, surface angle NPQ is pi minus AZ. Okay. And this angle is what? This is the angle between the solar projection on the horizontal plane and the global south direction. Okay. So, yeah, so that was a mistake I made. So, please correct it. This is pi minus AZ, and for the angle NOP, which is the central angle, that is pi by 2 minus L. Okay. Now, let us apply the cosine rule. Okay. If we apply the cosine rule, then this particular surface angle, central angle will be cos of NP cos of PQ. So, this arc on the surface, that means it is a central angle, okay, plus sine of NP sine of PQ multiplied by the surface angle, which is cos of pi minus Az. Okay. Now, if we substitute these values, cos pi by 2 minus L latitude, cos of zenith angle theta z plus sine pi by 2 minus L and sine theta z cos of pi minus Az, the solar azimuth angle. Okay. So, from here this is nothing but sine of delta, right. Cos theta is equal to sine pi minus theta. So, that way we can write cos L sine theta z cos Az. Okay. This minus sign is coming because of this term. Okay. Cos pi minus Az is nothing but minus cos Az, and that is why we are getting this. Okay. Now, what we can write is, we know that alpha, which is solar altitude angle, that is pi by 2 minus theta z, right. So, if we substitute that, what we get is sine delta equal to sine L sine alpha minus cos L cos alpha cos Az. Okay. That is another important angle that we obtain from the spherical triangle on the surface of the earth, okay, which involves all different angles, but it still does not involve the hour angle, which we will see very soon. Okay. So, let me stop here for this class, and in the next class we will continue using the spherical triangle on the surface of the earth, and we will connect the hour angle with these azimuth angles and get a completely general derivation that will be applicable anywhere on the earth for any surface, and that is our goal. Okay. Thank you very much for your attention.